This is NPS605W, and I'm measuring the ripple and noise using the differential method. Not 100% correct because the lines aren't terminated with the 50 ohm load, but for all intents and purposes, we have a more stable reading on our math function, and we're aiming for a cleaner reading, eliminating any common mode interference. So we're currently sitting at 9 volts. So if we turn up the output, and we can see that the math function is currently sitting at 100 millivolts. Let's have a look. Let's adjust that down. We want to adjust the math function down just a wee bit. Just move the offset, so just so we're sitting nicely within a division there. We'll continue to ramp up the power supply. We have a little bit of a peak and then it settles. I'm just doing the recalculation, and we're still sitting in, let's call it, we're still sitting in that 100 millivolt range. Mind you, this is no load. We do have some high frequency spikes. I'll try this measurement again with a 10 kilo ohm load across the output and just see if that helps. So we're not too worried about the channel in channel A and B, or the 1 and 2 channels down the bottom. This purple trace, or the blue trace in your case, is just a mathematical function of these two readings and gives us a more accurate reading of what noise we can see coming out of the power supply. So we're nearly at full scale. Our peaks are definitely increased, but the base ripple has remained pretty much the same, and that's full scale now. Okay, so I'll put a 10 kilo ohm load across the output, just like that, and it's made no real difference to the output. Okay, so the load is connected to the power supply. This is only really good for 175 watts-ish. I do have a load on the way that may make these tests a little bit more accurate, but for the time being, we'll see how we go. Okay, we'll wind up to about 5 volts. Again, it's a little bit hit and miss. The potentiometers aren't the best interface. In this case, I'd rather have probably a rotary encoder type interface, but potentiometers, for this price point, you're not going to get that. We're at 5 volts. We'll wind in some load. You just see there we're coming up to 1 watt. The current limitation on the power supply is screwed up to max. We're not too worried about that. We'll control that with the load. Okay, we're sitting at nearly 3 watts. And our ripple is increasing, so we're probably looking at, we're still averaging probably 100 millivolts, but it seems to be surging. Using this type of electronic load is probably not the best method, but it'll give us a rough idea on how this power supply would perform. So we'll wind up a little bit more current and see what we can get. Right, about 10 watts. Yep, 100 millivolts is still sitting at just the way it is. Keep going up. All right, we'll keep winding up the voltage on the power supply. Actually, we'll just bring that down a bit. We'll go to our next load. Let's go to 20 volts. Let's see where that sits. All right, wind in some load. Okay, we've limited. We'll just come back to the brink of limiting. Wind it back a bit. Okay, 5 amps at 20 volts, roughly sitting at about 100 watts. You can see our calculated noise, ripple noise, is sitting just outside probably 100 millivolts. It's probably not the most accurate reading without the 50 ohm loads in the scope leads, but it is what it is for the time being. Let's wind the load off. Right, let's go to 30 volts. There we go. Wind in some load. Let's approach 5 amps if we can. Okay, 5.1 amps, 154 watts. Again, no real change. Still sitting around the 100 millivolts, which is great. It's offering some sort of consistency, which is fine. Moving on, let's go to 50 volts. Again, we'll just go to our limitation of about 175 watts. Oh, just overshot. I'll back that off a bit. Let's wind that back in again. Okay, let's wind that in towards 175 watts. Sounds like a little bit of oscillation coming from the load. Okay, we'll leave it at about that. The noise signature is still probably maybe a little bit over 100 millivolts in this case, but the power supply is completely stable. Ever so slightly warm to the touch. The fan has not turned on as yet, and it is a temperature control fan, much like the NPS3010. So in this case, at all voltages, full scale, it does seem to be fine as far as being consistent on the ripple. Let's wind that back down and we'll go to full scale, 61.5 volts. Let's wind in that 175 watts again, ever so slightly. I might change these potentiometers out on the load to 10 turn pots. It gives a bit more granular adjustment. Okay, again, the top trace here is still fairly consistent. There is some spiking going on, whether that's transient or common mode, not sure. But if you look at the averaging across the center of the trace, it still sits at roughly about 100 millivolts, which is great. All right, now we'll do some overshoot tests. Okay, with the overshoot testing, we're going to use these banana jacks. They're audio speaker cable terminations. Can you see that? There you go. The only reason why I use these is just an easier way to clip on probes and loads and all that sort of business. So I'll be using these in the front jacks of our power supply. So they are very firm fit. So we should get good connections, and everything else that I want to connect to this, be it crocodile clips or probes, will work out really well. Okay, 5 volt, no load overshoot test. Trigger set to 1 volt. Oh. Okay, I'm just going to set the cursor up on this to maintain a point of reference. We'll set it to manual, and we'll set top and bottom. We shall toggle. Okay, 5 volts. And we peaked at 6.5. Same test again, reference marks. Again, 6.5 overshoot at 5 volts. Not great. Okay, third time's a charm at 5 volts. Again, 6.5 volt overshoot. Sorry, 1.5 volt overshoot on a 5 volt startup. So yeah, again, not great. 3 times, it's consistent, give it that. Volt overshoot test 1. I've adjusted the scale earlier to 5 volts per division. We do as an overshoot, so we'll adjust the top trace, the top cursor to the top of the waveform here, and that says 13.7 volts. So that's a 1.7 volt overshoot. It does taper off to the 12 volt mark, where it does start regulating properly. So in that time, it takes 200 milliseconds to settle. Okay, I'll leave my marker there. I'll get the other 2 out of the way. Discharging the output. Second test, 12 volts, turn on. Again, 13.7, top of the waveform. And test number 3. Exactly the same, 13.7. And then settles down to 12. So overshoot tests fail. Overshoot test at 30 volts, triggering at 10 volts. Here we go. Oh, the common theme. It's sitting at about 32 volts. Hold on a second. I've got cursor B is sitting at minus 200 millivolts. I'll just straighten that one up. Get that at 0. Here we go. Just move that window. Yeah, if we go to the top, just adjust that top cursor to just so it touches the top waveform. Yeah, 32.2 volts. Not great. All right, we'll do it another 2 times and go from there. So power supply off, same routine. Discharge, discharging with 820 ohm resistor across some multimeter leads just to make sure I'm under, oh yeah, that's 0.1 volts. Sorry, 0.01 volt, single shot capture, getting ready to go again. Second test, 30 volts. Yep, consistent, still sitting at 32.2. Turn it off, reset, discharge, 0.01. Ready to go again. Third test, 30 volts. And we have consistency. It's still sitting at 32.2 or 32.2 volts. So a 2.2 volt overshoot at no load. Okay, next test will be full scale at 61.5 volts. Okay, we'll quickly adjust our scale because we are measuring higher voltage. We may have to go to our times 10 on the probe and click times 10 on the probe. Scale our voltage down. Okay, 20 volts per division. because we are measuring 60 volts. So that'll give us a good scale to work from. We are going to trigger at, bring the trigger down to something more respectable. Let's trigger at 20 volts. Doesn't really matter as long as it's under our max. And just for shits and pickles, we'll change our cursor. Let's wager a bet. Okay, so we've got it set at 61.4 volts or 61.5, plus or minus, give or take. I'll go 62.5. No, let's go to 63. Set the top cursor to 63 volts. There we go. Oh, 63.2. I'm not going to muck around with it much more. All right, so we are discharged. Let's double check that. 0.003 volts. Nice. Okay, 61.4, 61.5 volts. Overshoot test. Single shot capture. Here we go. 2 seconds. My bottom cursor is sitting at plus 400 millivolts. That's no good. Got to change that. Just wind that down to 0. Perfect. Okay, 61.4 volts. Overshoot test. Ooh. Look at that curve. It's a nice, slow sort of curve on the voltage rise there. It tapers right off, but we have overshot just this minuscule amount. Let's go to the top of that waveform. It's only ever so slight, but if we were to measure it, we would say that was 64 volts. Well, there you go. At 61.4 on the power supply, we have a 64 volt overshoot there. So we're nudging 3 volts. So there you go. That's the no load overshoot tests. What we'll do now is cobble up some sort of load, not my electronic loads. This will be static loads, static resistive loads, and see how we go. So I'm quickly going to knock up a resistive load. I've got 4 of these 100 watt by 1 ohm power resistors, and I'm just going to make up a little test jig. So hopefully we can use a resistive load on our power supply test rather than a DC electronic load, which unfortunately is introducing some oscillations into our reading. At least this way, using power resistors, there's no way we can introduce unwanted signals. We can get a cleaner signal. So my plan is to put these in series, like so, and then we can step the connection between each point and test different loads. We got 1 ohm, 2 ohm, 3 ohm, 4 ohm in series, and really dial in a decent load up to 400 watts without having to introduce other unwanted oscillations into our reading. That's the plan, at least anyway. We'll see how we go. Okay, in the next series of tests, we're going to be testing the constant voltage and constant current capabilities of this power supply. We are testing constant current mode. We've dialed in 1 amp on our power supply off camera. We are running through a 4 ohm load, and we're going to capture the characteristics of the constant current limitation of this power supply. So we're currently set for 5 volts per division and a 50 millisecond window per division. Single shot capture, and we are ready to roll. Oh, that's pretty bad. Ooh, Okay, 21 volts to the peak, settled out at 4.1 volts, which is correct. And then we have undershot. Actually, we'll measure that from the other side. Change the cursor B, measure the undershoot. Okay, that's at 800 millivolts from off. Okay, so that would then state 3.9 volts undershoot. All right, we'll rinse and repeat and do the same for 2 amps. Actually, no, we won't. We'll do the same thing and we'll go into constant voltage mode. So we'll dial down the voltage until we just hit constant voltage. There we are. We'll go back a little bit. Okay, it's not gonna let us. Okay, constant voltage. I'll do the same trick again. This time we are relying on constant voltage, single shot. Make sure our trigger's set within our range. We'll set it to 2 volts. And again, our nominal voltage is 3.9, but we shot over to 5.3. Call it 5.3 volts. Okay, next we'll do 2 amps. Okay, you can see our power supply is now set for 2 amps and we're in constant current mode. What we'll do, we'll drop the voltage and just until we hit constant voltage. There we are. And then we'll repeat the same test as before. Well, getting pretty toasty. Okay, we are ready to capture constant voltage, 9.08 volts for a set point of 7.6. Okay, now we'll just roll the voltage up until we hit constant current. There we are. Turn the power supply off, reset our oscilloscope, and 2 amps constant current. Resting at our set point of 8.2 volts, and our overshoot was 10.48. Now we move on to 3 amps, just like so. 38 watts, reset. Let's change our scale to 5 volts per division, single shot capture, and turning on the power supply. Oh, it's like a set of stairs. Okay, it's constant current at 3 amps. Our peak voltage for a set point of 12.8 was 17.5 volts. Let's roll this down till we get to constant voltage mode. There we are. Power supply off. Wait a few seconds and turn the power supply back on. We did not trigger our voltage. Set it to 3 volts. Trigger. There we go. So for our set point of 11.5 volts, our voltage overshoot measures at 13 volts. All right, let's move to the 4 amp window. I've got to be careful here, I don't want to melt my bench. Okay, 72 watts. In fact, let's just roll off the voltage until we go to constant voltage mode and then come back just ever so slightly into constant current mode, like that, and we'll test that. Okay, turning on now, and same sort of waveform. We've got a slight overshoot in voltage. We sort of level out for a good 250 or 225 milliseconds, and then we drop off to our final set point. That's quite a delay for our constant current system to kick in. Just turn it off for a sec. This is getting toasty. Might just pop a heatsink underneath that. This is just before our 4 amp constant current set point. We are now dialed in the voltage just to sit below constant current. So this is a constant voltage test. As expected, slight overshoot. Our set point is 17.1 volts and our overshoot 18.8. Okay, now we'll move to the 5 amp test. And we're pulling 115 watts. Okay, we've just entered constant current. We'll turn that off, reset our oscilloscope. Okay, 5 amp test. Whoa. Okay, we've got that second step. I'll just get this cursor out of the way. We've got our overshoot, we've got our bit of a plateau, and then we're down again to our set point at 5 amps. Okay, what we'll do, we'll measure that overshoot. It says 25.8 volts. Whoops. Let me just reset our, see what's going on here. There we go. Okay, we'll just set so we enter constant voltage mode again. There we are. Turn off, reset. This will be the highest current limitation at given voltage on a load that's 4 ohms. Here we are, overshoot, plateau, drop, same profile, and sitting at 26.6 volt peak at a set point of 24.2. What I might do now is I'll ramp up full voltage, keep it in constant current mode, and have a look at the difference of our overshoot given a higher voltage set point. What I'll do, I'll dial in 10 volts per division and we'll go from there. Let's see if having a higher overhead for our voltage has an effect on the overall overshoot. And that's an astounding yes. So let's drop back to have a look at where we're sitting. So if you do have a higher voltage and you're relying solely on your constant current, the more overhead you have set in your voltage, you will have a higher overshoot when you initially turn on the power supply. So our set point is 24.5 volts under constant current, and yet our peak overshoot was 37.4 volts. Definitely has the potential to destroy any device under test. So that pretty much concludes the constant current and constant voltage tests. I'll have to shut this down because my these sinks are actually getting quite toasty. For an $80 lab power supply, it performs quite well. It's not even warm to the touch, to be honest. So whatever switching elements they're using in there seem to be high quality. We do know that it's got a good quality switching IC in there, and generally it does the business. Just be mindful that its constant current and constant voltage modes aren't the best. Probably not a good idea to have your device under test straight away. Have your voltage set to just where you need it, rather than rely on the constant current to save you. This pretty much concludes the testing of the Minleaf NPS605W bench power supply. Thanks for watching. If you enjoy my content and want to see more reviews, repairs, and general maker stuff, please consider subscribing and clicking that bell icon so you get notified when I upload new videos. Also consider following me on LBRY, otherwise known as Library, where you can find the exact same content while contributing to the channel. Thanks for watching. Okay, overshoot test at 30 volts. Zip. We'll wind. Oh, fuck no. Oh no, we were recording. Ah, fuck. Scrap this. Relating to constant current mode.